All right, we're looking at Darcey's formula sheet for exam 2 in supply chain 303. She's got some definitions at the top. Population, complete set of n items, that's fine. Sample proportion subset of the population select for analysis. That's ignoring bias. You want your sample to reflect the population. If it doesn't reflect the population, you have bias. And it's also ignoring the whole existence of the central limit theorem. Okay? Random sample, a sample of size n drawn from n items in such a way that each of the n items has the same chance of being selected. In other words, she's saying each sample has an equal chance of being selected. That's all that says. A variable, it's a characteristic of the item like height, weight, gender. Population parameter, that's a number from the population. A sample statistic's a number from a sample. In other words, a population means a parameter, population standard deviation is a parameter, sample size, not size. Sample size is not a statistic. Sample means sample standard deviation or statistics. She has the average standard deviation equations right here. The only reason they should be there is to make you calculate some stuff by hand. If you've got a good old TI-30, especially this one, most of the TI-30s will do it. This one does it real easily. I'm going to make a video on how to do this one in a little bit and post it. Okay? And then she's showing all the different symbols for the different notations. Here, she has population here. These are her parameters. She has sample here. These are her statistics. Okay? And here she's starting to talk about central limit theorem a little bit. She's starting to say, well, capital X bar is an estimator of the unknown population mean. That's the first part of central limit theorem. S is an estimator of the unknown sigma. For large sample size, X bar and S will tend to give better estimates of the parameters. And right here she's saying unbiased. Here she's saying standard error. Over here she's saying standard error, which she promptly ignores in some problems and does something else. So that other equation is not here. And then central limit theorem, X bar behaves more and more like a normal. With the variable n increases, we assume n over 30 is sufficient. The sum of the average and the normal distribution has a normal distribution. The sum or average of a normal distribution has a normal distribution for all n greater than or equal to 1. In other words, if it starts normal, it stays normal. A normal distribution, we do not need a large n. If it stays normal, it's normal again. Here she's doing finding z for a standard normal distribution. I keep mine to x minus the mean over standard deviation. And we just calculate standard deviation from these up here. Okay? Expected value is the sum of n times mu. That's weird to me. That's only on categorical. That's not on numerical. The expected value on numerical is the big X bar. So this is weird. And the standard deviation is the sum of this. Okay, now what I think she's talking about here is she's talking about for the central limit theorem. Again, this doesn't make any sense. That makes sense for categorical, not numerical. That doesn't either. Okay. Now down here she's defining its categorical. On categorical, those could make sense. But not on something that's numerical. It does not. So let's look at the second page of this thing. And I don't know why there's a blank page between them. Or what is going on with that. And up here, she is doing the weirdness I was discussing. Okay? Right here, she's saying standard error is the square root of np and 1 minus p. And over here, she's saying standard error is the square root of p, 1 minus p over n. She's got two different standard errors right there. And you can't do that. She is. So what she's going to do is set it up so you have to work it her way on a test. This one over here is for counts. And this one over here is for percents. Proportions. Okay? And then she's got the standard confidence interval things. This can be found on the bottom row of the t-table. And I just look at the t-table for this. I don't ever look at the z-table. These values replace z in the general formula, if valid. Confidence intervals for n greater than 30. She's showing you the two, but she's leaving out on this one that it must state on the t. Wrong one. I'm circling the wrong one. On the t distribution, must state normal. She's leaving out that it must state normal right there. N is less than 30, yes, but if it doesn't state normal, you can't use it. So she left that out. She leaves things out of her formula sheets all the time. Okay, characteristics of the t distribution. We have sample size n, that n has n minus 1 degrees of freedom. Technical assumption, the values must be drawn from a normal distribution. This is crucial only when n is small. See, she does say it here, but not up here with the equation like she should. Because you're going to look there for the equation. You're not going to read this. Sample size determination. She's got her two sample size equations. Nope. The other one's down here. This is not sample size. Okay. This is a confidence interval right here. And my sample size equation, I do z sigma over e squared, less math. This one here, I do z over e squared times p times 1 minus p, less math. Same answer, doesn't matter. I'm used to using m's down here for margin of error instead of e for error. Okay, now what she's telling you here is you have to know the population standard deviation to find the sample size. That should be given in the problem. Down here, if the sample size is not given, if p is not given, you assume p is 0.5. All right, there's a quick rundown through her equation sheet. It is missing a few details. This is apparently she's been working on her formula sheets and trying to make them better. This one isn't horrible. All right, I hope you enjoyed. Hopefully you find this useful. And I will get the video to you soon.